All right. Hey everyone, it's Matt. Today I want to go through the first little bit of Unit 2. We're thinking about probability. We'll go ahead and introduce a couple of concepts and ideas in this video, and then in class we'll go into more detail. Things can get a little more complicated. In probability, we're thinking a lot about experiments and random experiments. So this is some kind of event that we can't control and we can't predict. We're not sure what's actually going to happen, but a number of things could happen. We often denote the sample space by S. So this is, as we say, the set of all possible outcomes for a random experiment. So for example, as we say, maybe the roll of a single fair die is a random experiment. There are a couple of options we have here that could happen as the outcome, and so we take our sample space S to be the face could show number 1, 2, 3, 4, 5, or 6. These are the options for us. Similarly, we could maybe flip a single fair coin. The options here being we either get heads or we get tails. We can write it like this. Okay. We could maybe flip 2 coins. In this case, we'll have more options available to us. You can imagine having 2 heads. We'll use H for heads. We could have a head and a tail, tails and heads, or 2 tails. Let's just record here. So as we said, H means heads and T means tails. Now we could have just written this in words to say, oh, we could get 2 heads, 2 tails, or 1 of each. But we will find when calculating probability, it's more convenient to separate things out in this way, to write heads and tails and heads separately as they appear from each coin. Now, so that's the sample space. An event is a specific outcome of a particular experiment, and this is some subset of the sample event. And we'll call that event simple if there's only one element in this sample space. So if there's only one particular outcome in our event, then we would say it's simple. So again, for example, if we roll a single fair die, our S, or sample space, is going to be the numbers 1 to 6. An event, some subset of this, we could require or desire to know about rolling just an even number, 2, 4, or 6. Similarly, we could have an even smaller event, B here. This is just to roll a 2. This one has only a single element, so we call this a simple event. Sometimes you might call this event like a compound event. That's not super common though, but if you see it, that's what it means. Okay, so let's do a couple more examples here. So we can bring back our flipping of 2 coins example here, where we said the sample space looks like this. We could consider the event C, flipping exactly 1 head. Which would include these 2 options here. Or perhaps we could think a little bit bigger and consider getting at least 1 head, which would include the 2 above, but also the double. All right, let's keep going here. You can imagine instead of rolling 1, we can roll 2 fair dice. Each die has the numbers 1 through 6 on them. Now, there's a couple different ways we could consider the sample space here, depending on what we're interested in. So actually, let's think about two different sample spaces. So you might be interested in the total of the two dice together, that is, add up the result. We could maybe call this one S1. And these would give us the numbers 2 through 12. So the smallest we could get would be snake eyes, and we would go all the way up to double sixes. This one's kind of fun in terms of probability. That's one way we could imagine representing the sample space. Alternatively, we could look at just the values shown on the two dice. So this is kind of like our coin example before. So there's a number of possibilities here. You can imagine we could get both ones. We could get a 1 and a 2, a 1 and a 3, 1 and a 4. This continues ad nauseum. That's all the ones. We could have 2 and 1, 2 and 2, and it just keeps going all the way up to 6 and 6. There's a bunch of possible outcomes. We have 6 outcomes for each. So this is a total of 36 possible outcomes. That's probably too much to write out by hand. We can consider this event here, roll a 7 or an 11. We can represent that event in this way. This would be in terms of S1, of course. Let's move to event B. You could be interested in rolling doubles. Both dice have the same number on them. This is not really possible to write in terms of S1. The sum could be a number of different things depending on, and it doesn't really depend on whether you roll doubles or not. But we can write this in terms of S2 in the following way. We're requiring doubles, so we have 1 and 1, 2 and 2, 3 and 3, all the way up to 6. And as we say, this is in terms of S2. Okay, so when we're thinking about a particular event, we may be able to assign an event with its corresponding probability. So for a given event A, P of A is its probability. This is the chance that this event A will occur. Probabilities are going to range from 0 to 1 or from 0 to 100%. If we say P of A is 1 or 100%, we will say that if the event is certain to occur, if we know it's going to occur. If the event is never going to occur, then we can say its probability will be 0, or we might say 0%. As a rule, to be considered a probability, we need the P of A to be between 0 and 1 inclusive. I'm not sure what it means to have negative probability, and it doesn't make much sense to have probability greater than 1 either. Now, there's mostly two approaches to probability. Classical approach is, well, the classical one. We've been using it for a long time. The idea is to think of your experiment as having a number of steps, each which has an equal chance of occurring. So if we can break our experiments up into simple events with equal chance of occurring, this is important here. Otherwise, you can't apply this approach. But if you can just take the number of ways that the event can occur and divide it by the number of total simple events, the total number of things that could occur. So for example, let's come back to rolling a single die. We have these 6 possible total options here, and our event might be rolling a 3. It's a simple event. The option is only the 3 here. We could consider the probability of A. That's going to just be, as we said, using the classical formula, S over N. S here is just 1. We have 1 total outcome in our event. And the total number of possible outcomes is 6. There's 6 sides on our die. Total number of simple events. Okay, we can take the ratio here, and we get about, well, we get 1 on 6, which you might sometimes write in this way. So that's 0.16 repeating. Or for us, we can maybe round to 4 decimal places, 1667. So let's just, for ourselves, know, let's keep at least 4 decimal places. Okay, we could do another one. We can consider the event B, roll a number greater than 2. So this is a little bit larger. Rolling 3 is greater than 2, but so is 4, 5, and 6. Here we have a total of 4 outcomes in our event. N is still 6. And so the probability of B is 6 over 4, or 2/3. We can write that as maybe 0.6667. All right, so that's the classical approach. It's rather familiar and has existed for a very long time. The other approach, the relative frequency approach to probability, is becoming or has become more common in the past maybe 20 to 30 years. This is largely due to computing. So let's think about this method here. The idea is basically brute force. So you somehow conduct or observe the experiment a large number of times. This is important here, large number of times. And you simply count. You keep track of how many times your events occur and how many times your events not occurring. Then we can think about the probability P of A as just being that ratio there. So as you can imagine, with the speed and ease of use of computers these days, people are finding this method a little more popular. You can just write a couple of loops, have your program crunch through some things. You can perform millions of experiments quickly and get a pretty good idea. Notice the approximation here, get a pretty good idea of the probability. Okay, so let's see an example here with a coin toss. So maybe we're considering just a simple coin toss and we're wondering if we're going to get a head on the coin. If we repeat this experiment, maybe I did this earlier, you can toss a coin 5 times and maybe I got 2 heads coming here. That's something like 0.4. Now we know that the probability here is supposed to be 50%. Of course, the problem is we only conducted 5 experiments. That's not really a large number of times. But you could imagine that maybe I don't have a lot going on. I toss the coin 50 times, comes up 28 times heads. That's getting a little bit better, it seems. That's something like 0.56. So we're getting a little bit better there, but we can keep going and conduct this experiment over and over. Maybe we throw 5,000 and get a little over 2,500 here. Now we're on to 501. So you can see what's happening here. We're getting closer to 50%. And you can imagine throwing this very large number of times and getting pretty much half of them heads, as we see here, for a grand total of 0.5, a bunch of zeros. And so this number is very close to 50%. And so you can see the pattern as we conduct this experiment more and more times. The total estimate for the probability of A is approaching 50%, which we know to be the true probability here. So we're approaching 0.5. So let's note that as the number of trials n is getting large, as n goes to infinity, our P of A is approaching the true value. Now, there are some interesting questions about, well, how do you know when you're done? How do you know when the values have kind of stabilized and stopped changing and we can stop doing more experiments? Isn't it always better to do more? Shouldn't we just keep going forever? These are things we can maybe talk about a little bit later. But for now, let's just remark that this relative frequency method will approach the classical value. Classical value. Okay, so if, for example, we wanted to experimentally determine the probability of rolling doubles when rolling 2 dice simultaneously, we would repeat this experiment many times and then count the number of doubles. How many times do you need to repeat this experiment? I mean, probably at least thousands. We can do this many times. We could count the number of doubles and then compare that to the total number of experiments that we did, the dice that we threw, and get a ratio there. We would do this many times, probably, I mean, at least thousands. We would probably want to do that using a computer, but we can think about the classical approach as well. So here, we've thought about this a little bit already. So the sample space consisted of 36 simple events, 1 and 1, 1 and 2, all the way up to 6 and 6. All of these events are equally likely, so we're in good shape to use the classical approach. We're interested in this event E based on rolling doubles. So we've seen there's about 6, well, there's exactly 6 of these, 4, 5, and 6. Simple events, and so the probability of this event is going to be 6 over 36, or about 1 or 1/6. You can imagine amusing yourself with randint or something, writing a couple of loops and doing this experimentally, and you can see kind of how long it takes you to approach 1/6. This idea that we're talking about here, where the experimental probability will approach the classical one, this has a name. It's called the law of large numbers. The relative frequency is going to approach the actual probability, which is the classical probability that we've been talking about. So this graph here is an example of this. So the x-axis here, this is actually some experiments on number of coin flips. And you can see here that, I mean, it looks like we started out maybe getting ahead, but it jumps up and down. Eventually, we're starting to approach .5, which is what we expect. This axis on the y-axis, this is proportion of heads. Okay, so we can think about another example to demonstrate this. So you may wish to find the probability of rolling a 3 on a single die. One could take the relative frequency approach here, roll a die many times, and record the number that we get. So this is like our previous example here. Maybe you roll 10 times and you get 2 3s. That's what you observed. We're looking at about 20% here. If we continue, we roll 100, we get about 14 perhaps. And for about 14%. If we keep going up to 1,000, it looks like we're getting maybe closer to 16%. So it's kind of jumping around here, going up and down, but you can see as we go, the probability is approaching our classical value. We expect this to be somewhere around 16%. We've seen this one already today, so that's 0.1667. We've denoted that here anyway. Oh, I'm breaking the rule in rounding to 3 decimal places. For rolling a 3, 1/6%. Okay, and we think things should get better as we increase the number of trials. All right, let's wrap this up with one more example here. So maybe we're using these playing cards here, and we're interested in getting what we can call a flush. So that would mean all the same suit. So this particular hand here is a flush. It's got all clubs. Maybe you do or don't play cards. There are 4 suits, and each suit has 13 cards. The other suits being hearts, spades, and diamonds. Okay, so maybe you're playing this game, 5-card stud poker, not the most popular poker, and you want to know this probability here. Apparently, according to this particular official rules, there are a total of 5,108 different combinations of cards that will produce a flush out of a possible maybe 2.5 or so million possible rearrangements of cards. So this probability here of getting our event, which is the hand of flush, is going to be the ratio of these two numbers here. 6, 0, which is pretty small. Yeah, less than 1%. Looking at 0.1965% chance. So probably not going to happen all the time. Sounds like a pretty good hand. You could try the relative frequency approach here, so we could play a bunch of games. You may play thousands. You maybe even want to play somewhere up to 1 million. Probably we would prefer to do this using a computer. And we could maybe write some kind of conditional thing to investigate and count based on the outcome, whether or not it's a flush or not, keep a running total, count how many flushes occur, and compare that with the total number of trials that we've done. So you could probably do that now to do the relative frequency approach. The classical approach, once we get a little bit more in this course in terms of combinatorics, we will be able to do this. For now, coming up with these numbers here may be a little bit challenging, but we will eventually be able to do that by the end. So you can look forward to this. Okay, we'll pick up here in class and continue thinking about probability. We'll see you later.